Good afternoon, all of you. So today class is mainly focused on some important examples on transformation on continuous random variable. In the last class, we talked about some example. There was also some examples on continuous and discrete. There are some problems on probability mass functions, probability density functions, and what are the conditions of a possible PMF for a possible PDF. And also we have discussed about some geometrical problems, mainly based on the uniform distribution. So today we'll have more important examples on continuous random variable. So first example is that let x be a standard normal variate. X be a standard normal variate. And you know what is the PDF of the standard normal variate? That is e to the power minus x square by 2 by 1 by root over 2 pi. And find the probability density function of y. Find the probability density function of y where y equal to half of x square. So your problem is x, a random variable x which follows a standard normal distribution, and you have to find out the probability of the function y. So your x follows standard normal distribution. You know, for standard normal distributions the parameter are 0 and 1. M is 0 and sigma is 1. M is called the mean of the distribution, sigma is called the standard deviation of the distribution. So we write symbolically by this, x follows standard normal distribution. You have to find out the probability density function of y. So before we start the solution of the problem, we have to know what is probability differential. So let x be a real number and delta x greater than 0 positive, such that derivative of f dashed exist in x comma x plus delta x. In this interval the derivative exists. Then the Lagrange's mean value theorem, we can find a theta very small, 0 to 0 less than theta less than 1, such that probability of x less than x, capital X less than equal to small x plus delta x is equal to f of x plus delta x minus fx, that is the increment, equal to delta x f dashed x plus theta delta x, that is from the Lagrange's mean value theorem. And if you take the limit on both sides, that is delta x tends to 0, if you take the limit on both sides and dividing by delta x tends to 0, then we'll arrive at this important relation, that is probability of x less than equal to x plus delta x equal to fx dx. This is called the probability differential, that is derived from the Lagrange's mean value theorem, taking limit on both sides. This is called the probability differential. Okay? So we'll use this probability differential in the solution of the problem. So now let's start. So you're in real variable, because in random variable we can write y equal to half of x square, right? This is in random variable. And in real variable we can write small y equal to half of x square, minus infinity less than x less than infinity. Then your dy dx is given by x, and let fx and fy be the density functions of x and y respectively. Fxx is the density function of x, fy is the density function of y. So suppose x greater than 0. First case, let x be positive, because your interval is minus infinity to infinity. Let us take two cases on this. First we'll assume x greater than 0. So we have probability of y less than capital Y less than equal to y plus dy equal to, your y is half of x square, so we can use the transformation y equal to half of x square. So half get cancelled from all the sides, and you are remain with f probability of small x square less than capital X square less than equal to x plus dx whole square. Okay, this is a simple calculation. Now this square inequality can be written as small x less than capital X less than equal to x plus dx union minus of x plus dx less than equal to capital X less than small x. This square quantity can be written as like this. Now these two events are mutually exclusive. This and this are mutually exclusive. So we can write probability of x less than capital X less than equal to x plus dx plus the other part minus of x plus dx less than equal to capital X less than minus x, less than minus x. So, but due to symmetry of the standard normal curve, you know that standard normal curve can be drawn like this. This is the standard normal distribution. This is your 0. This side, the left hand side of the y-axis have 50% data, and the right hand side of the y-axis has 50% data. So total area is approximately equal to 1. So this is symmetric about y-axis. So due to the symmetry of the distribution, we can write this negative quantity also equal to this. So we can write this due to symmetry of the distribution. Okay. So twice, so we are arrived at p of y less than capital Y less than equal to y plus dy equal to 2 twice p of x less than capital X less than equal to x plus dx. That is due to symmetry of the distribution. Now, this is nothing but your probability differential, right? Look at that. Probability differential. Probability of x less than capital X less than equal to x plus delta dx is nothing but equal to fx dx. So this is your probability differential. Therefore, your left hand side is fyy dy and right hand side is twice fx dx. So fyy equal to twice fxx dx dy. And what is your dx dy? Already you have calculated. Look at that. Your dy dx is given by x. So your dx dy equal to 1 by x. And also your fxx. Your fxx is given by e to the power, that is the probability density, the PDF, probability density function of the standard normal curve, is given by 1 by root over 2 pi into e to the power minus x square by 2. Minus infinity less than x less than infinity, right, for all real x. This is the PDF, probability density function of x, random variable x. So you look at that, you have this, then if you substitute fx, you will have 1 by root over 2 pi e to the power minus x square by 2 into 1 by x. Okay. Now if you change your x in terms of y, what is your y? Y is your x square by 2. So x will be root over 2y. Root over 2y. And this form, this fx, x, if you replace your x with y, you will have this type of relationship. You have a gamma and e to the power minus half minus y, y to the power minus half. 0 less than y less than infinity. Because you have a square root. Because you have y equal to half x square. So x equal to, you can easily convert this, right? So you will have this. So this is y is a gamma half variate. Y is a gamma half variate. Y is a gamma distribution in that case. So that is a very interesting fact that when your transformation is y equal to half x square, in that case your standard normal distribution transformed into gamma distribution. And this is your gamma half variate. Similarly, if you take the case of x less than 0, because we have drawn the case for x greater than 0, if you evaluate for x less than 0 using the probability differential and the same process, you will arrive at that this is also follows the gamma half variate, gamma distribution. And this is your y is a gamma half variate. So in both the cases we have the same result. Okay, this is one of the important problem of the transformation. Let's have another problem. Example 2. If x is uniformly distributed in the interval -1 and 1, then find mod x. Find mod x means the distribution of mod x actually. Then you have to find out the distribution of mod x. So here x is uniformly distributed. Its probability density function is given by, for a uniform distribution, b minus a. B minus a less than x less than b, right? And 0 elsewhere. So that is equal to 1 plus 1, that is half if -1 less than x less than 1. And 0 elsewhere. So this is the distribution of x. Right? This is the distribution of probability density function of x. Now we have to find out the density function of mod x. So we have y equal to mod x. In real variable y equal to small y equal to small mod x. So dy dx is equal to 1 for x greater than 0 and dy dx equal to -1 for x less than 0. Because you can split mod x into two parts, x for x positive and minus x for x negative, right? You can split it into two parts. And fx and fy be the density functions of x and y as usual. So case 1, let 0 less than x less than 1. So you have the interval -1 to 1. Let's have the positive part first, 0 less than x less than 1. So we'll use the probability differential once again. So let us have probability of y less than capital Y less than equal to y plus dy. And y is your mod x, right? Y is your mod x. This is in random variable. In real variable, y small y is equal to small mod x. So you transform, and in this case x is positive actually. In this case x is positive, right? So we can write small x instead of mod x, x less than mod x capital X less than equal to x plus dx. Again using the same concept as the previous, we can write this can be written as union of these two events. And these two events are mutually exclusive, right? And this distribution is symmetric. So you have the same result as the previous one, already discussed in the previous problem. So you will use that symmetry and the use of that probability differential. We can write this is your fyy dy, left hand side, look at that. And your right hand side will be 2fxx dx. So fyy equal to 2fxx dx dy. And your fxs is 1 by 2, 2 into half, and dx dy is 1 for x greater than 0. Look at that, already evaluated, dy dx is 1. So dx dy equal to 1 for x greater than 0. So fyy is 1 for 0 less than y less than 1. Y is uniformly distributed over the interval 0 to 1. So in this case you have y is uniformly distributed over the interval 0, 1. Next, take the next case. Similar process will follow. Let us take the negative half, that is -1 less than x less than 0. Again using the same process, you will have this. Then you can write using the probability differential to fyy dy equal to minus 2 fxx dx. So again you have a minus plus. So you have a 1 because your dx dy is minus 1 if x less than 0. And here x is negative. Here x is negative. So x is negative, that is why mod x is minus x. So you have this negative, this interval. And this interval can be written as the union of these two intervals. These two intervals are again mutually exclusive. Again using the symmetry, you will arrive at this probability differential equation. And fyy is given by, in this case also, 1. So in both the cases, y is uniformly distributed over the interval 0 to 1 because your y is mod x. So I was searching for mod x, the distribution of mod x, right? Look at the question. Find the distribution of mod x. So you have x is uniformly distributed in the interval minus 1 to 1. Your mod x will be distributed uniformly in the interval 0 to 1. Okay. Next we have a more interesting problems. Yeah. The random variable x has the probability density function fxx equal to half e to the power mod x minus mod x. Find the probability density function of y equal to x square. Y equal to x square. Okay. So your real variable is y equal to x square. Okay. And dy dx will be 2x, which changes sign in minus infinity to infinity. Then if again by the same process, I am not discussing the process of probability differential. So you take the case of x greater than 0. I am just giving you a hint to how to solve the problem. You take the case of x greater than 0. Then using the probability differential, you will arrive at this equation using the probability differential, this relation. And if x greater than 0, sorry, this will be if okay, this is the case I am going on, the x greater than 0, your fyy will be this 1 by 2 into root over y e to the power minus root y, 0 less than y less than infinity, positive half. So this is your fy. Again, if you take x less than 0, the case of x less than 0, similarly you will go through the similar process, you will arrive at this type of distribution. Okay, this type of distribution. So ultimately your fy will be 1 by 2 into root over y e to the power minus root y, and 0 less than y less than and 0 elsewhere. So this is the distribution in both the cases, right? These are the three most important problems. Let us have more problems on that. I will give you more problems on that. Example number 4. The random variable x is uniformly distributed in 0, 1. Find the distribution of y equal to minus 2 log x. ln, actually e base. So your fx is given by the probability density function of x. It's uniform distribution, so it is 1, 0 less than x less than 1, right? And what about your y equal to this? In real variable it is y minus 2 ln x, right? And your dy dx will be, what is your dy dx? Dy dx will be minus 2 by x, and this is less than 0, negative for every x belongs to 0 to 1. For every x belongs to 0 to 1, let me add a page here. Okay, so this is your dy dx. So we can write fyy, the probability differential of y, equal to fxx using the transformation formula mod dx dy, right? Okay, and this is equal to, you look at that, your dx dy will be fxx is 1 into mod dx dy will be mod x. Okay, your x dy dx will be 2 by mod x by 2, right? And you can change your x, by using your actually x will be e to the power, x will be half e to the power minus half y, right? E to the power minus half y. This is your x will be this. You have a 2, so your x will be not half, only e to the power minus half, and because of this 2 you have ultimately half e to the power minus y by 2. So this is the distribution, and y ranges from 0 to infinity. Okay, so in this case your distribution is given by fyy equal to this. Fyy equal to, you write the final step, half e to the power minus y by 2, 0 less than y less than infinity. Okay, this is the case. So this is very simple. Next, we have another one. PDF of a continuous random variable x is given by, the PDF is given by 2x e to the power minus x square if x positive and 0 elsewhere, find the distribution of x square. So in let y equal to x square, in real variables y equal to small x square. So let me add a page here. So dy dx equal to 2x, and this is positive for all x greater than 0, right? And now fyy is given by the formula of the transformation fxx mod dx dy. So your mod dx dy and fxx is fxx is 2x e to the power minus x square into 1 by mod 2x, right? And that is equal to, you see, this is your distribution is given here, and this is equal to, because x is positive, when x greater than 0, you have only e to the power minus x square, right? These two terms will get cancelled. So that is equal to e to the power minus y. Actually y is your x square. Look at that, y is your x square. So that is equal to e to the power minus y when y greater than 0. Okay, this is how. So your fyy, finally the distribution is given by this. This is your problem number 5. We'll have another problem in this lecture. Problem number 6. If x is normal 0, 1, find the distribution of e to the power x. That is the standard normal. If we are talking about normal 0, 1s, that is x follows standard normal distribution, and then we can write this, x follows standard normal distribution, and that standard normal density function is given by 1 by root over 2 pi e to the power minus x square by 2, minus infinity less than x less than infinity. This is the standard normal density function. You have to find out the distribution of e to the power x. You have to find out the distribution of e to the power x. So in this case also, your let y equal to e to the power x. So in real variable it is given by y equal to e to the power x. Now what is your dy dx? Dy dx is e to the power x, and that is positive for all x belongs to R, right? For all x belongs to any real number, it is positive. Any real number, it is positive. Again, if x varies from minus infinity to infinity, y varies from 0 to infinity, right? So you can write that thing here as x varies from minus infinity to infinity, sorry, right, y varies from, actually y is your exponential function, so exponential function will varies from 0 to infinity, right? You got a range for y. Now the distribution of y is given by the notation is fyy, that is the probability density function of y, and that is equal to fxxx mod dx dy, that is the transformation rule. Okay, now your fxx is the standard normal distribution, that is root over 2 pi e to the power minus x square by 2 into dx dy is e to the power minus x, because look at that, your dy dx is e to the power x, so dx dy will be e to the power minus x. So ultimately if you change into y, because your e to the power x is y, so this can be written as 1 by root over 2 pi into 1 by y. This is your y, actually 1 by y, so I am writing 1 by y, and x will be given by log y, because look at that, e to the power x is y, then x is your log to the base e, right? So this can be written as e to the power minus log y, that is ln actually, not 10 base, by 2. So this is more compactly you can write fyy 1 by root over 2 pi into e to the power into e to the power minus log y whole square by 2. This is all the whole thing in the exponential power upon y 0 less than y less than infinity. So this is the distribution. This is the probability distribution of exponential e to the power x. This is the distribution of e to the power x. So these are the 6 important problems I discussed about, and we can discuss more on that. You will have, let me give you more as an exercise so that you can do that. So in this lecture actually I was talking about mainly on continuous distribution. We can discuss about the discrete distributions also. There are some problems on discrete distribution. So I'm just giving you 2 problems as an assignment for all of you. You can try this. So let me write the problems. So example 7. Find the, this is for discrete distribution of the square of a Poisson distribution. Poisson mu variate. We can write variate, that is the Poisson distribution. We can write here the mu, Poisson mu variate. Okay, that is the question. That is one of the, so find the distribution of the square of a Poisson mu variate. So what is your Poisson mu? I'm just giving you a hint for the how to solve this one. Probability of x equal to y. What is the PMF? Probability mass. This is the discrete distribution. I was talking about continuous. All the problems are discussed here are the continuous distribution. But this is the problem of discrete distribution. How will you solve? I'm just giving you a hint. So what is your PMF? Probability mass function of the Poisson distribution. That is equal to probability x equal to I e to the power minus mu. Mu is the parameter of the Poisson distribution. Mu to the power I by factorial I. Right? I runs from 0 to 0, 1, 2, 3, etc. Right? This is your Poisson mu distribution. Now you have to take y equal to x square, right? You have to take y equal to x square. This is the hint for you. So you have to take y equal to x square. So naturally this I will be I square, 0 square, 1 square, 2 square. So you have to calculate probability of y equal to I square, okay, and that is equal to probability of x square equal to I square. This is the hint. You try to solve with this hint, you will have some result on that, okay. So you can check that. Let me give you another problem. So this is the hint for problem number 7. Example 8. Example 8 is, this is also very important problem. You have so many. X is a Poisson variate. So your random variable x is a Poisson variate. Variate with parameter mu. With parameter mu. Show that probability of capital X less than equal to n equal to 1 by factorial n mu to infinity, integration mu to infinity, this is a improper integration, e to the power minus x, x to the power n dx, where n is a positive integer. You have to prove this, where n is positive integer. N is a positive integer. N belongs to the positive integer. So x is a Poisson variate with parameter mu, and show that probability of x less than equal to n equal to 1 by factorial n mu to integration mu to infinity e to the power minus x, x to the power n dx. N belongs to the positive integer. This is extremely important problem. This is also. So you try this problem. So I stop my lecture here. This is an assignment for all the students. Try to solve this. Otherwise you can contact with me. So you follow my next lectures in my channel. You can subscribe my channel. So I shall be talking about in some more distribution or about mean and variance of the distribution in the next video. Okay. So I'll stop here. Thank you all of you.